All right, we're back recorded. Here's Maxwell's Demon. All right, so that's on a little bit more, but okay, fill in some details here. All right, so the premise of this experiment. Now let's put a couple boxes next to it. Let's draw a fish tank. All right, so you guys can take the ruler on your desk, start drawing a rectangle. Help you guys draw this rectangle. All right, so great, got a rectangle. All right, you guys got a rectangle on your paper? All right, got a rectangle there. All right, then let's do an offset rectangle. So kind of maybe up and to the right. All right, new rectangle. Boom, boom. All right, oh, I got 2 rectangles offset. Connect the corners. Boink, 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 boink. Oh, there's a fish tank. Okay, there's also this partition in the middle. Let's get the partition going. Boink, 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 and boink. All right, there we go. There's our fish tank. Okay, could be maybe a hot tank next to a cold tank, possibly, maybe something like that. Right. Now, you guys remember back a few months ago when we were studying laws of thermodynamics. See, the first law of thermo said what energy is conserved. You can't create or destroy energy, but you can transfer it different forms. That's okay. Now, the second law of thermo, that's that's our focus here, says that processes have a certain time order. You can stir milk into coffee, but you can't unstir it out, right? And so as time moves forward, entropy in the universe overall increases, right? Even if entropy decreases within a smaller system, that system's got to be open so that in the universe overall, entropy increases as time moves forward, right? Now, this is really a statistical probabilistic law of nature, right? You can't, sometimes down in quantum systems with just like a few atoms at a time, every once in a while, the second law doesn't 100% hold up, right? This is one of those laws of physics that's almost like asking to be broken. And Maxwell had this idea of how that could possibly be the case, right? So it goes like this, right? Suppose you have a hot tank next to a cold tank. You would naturally expect, if you leave this alone a while, maybe the water mixes and you get like lukewarm. But you couldn't start with lukewarm water and walk away and come back an hour later and expect it to spontaneously separate. So you got the hot on one side and the cold on the other, right? Now you can force that to happen. That's what refrigeration is. That's what air conditioning is, right? But those are energy intensive processes, right? But Maxwell's saying, hey, what can you do this with just information, right? No energy input required, right? So let's draw a little demon here. It's got a little pitchfork, that, right? And this little character, he's in control of this partition. Let's say 0 net energy to operate. So whatever energy it takes to open the partition, you get it all back when you close it, right? So, right. And he's letting all the fast moving molecules to one side, right? So eventually they'll all build up here, right? And he's letting all the slow moving molecules to the other side. So velocity streaks, slow moving, right? Now, if you remember kinetic energy theory of temperature, right? That the faster on average that your molecules are moving, that's going to correspond to a higher temperature for that material, right? Okay, so now the left becomes hot and the right becomes cold. Well, what could you do with this? Well, it's like building an oven next to a fridge, right? Or, hey, could you use this to like boil water, turn into steam, turn a turbine, get, generate electricity from that? You could run power plants with nothing but information. You don't need any fuel source, right? So Maxwell set down this idea, and then took people over 100 years to figure this out. What was the answer to this, right? Can you really run a power plant with nothing but information, right? So here's the premise. Fast particles to the left, slow particles to the right, right? Would this break the second law of thermo? Could you possibly do that? This was a legitimate question for a long time. Conclusion they came to was no, right? Because, right, I'm going to add a little bit here. Right, there's a Landauer limit. Landauer limit. I looked this up. It's 0.018 electron volts. That's a tiny, tiny, tiny amount of energy. Okay? That's the energy it takes to erase 1 bit of information. Right? So, like if you look at a computer file and it's like so many megabytes or something, right? Megabytes composed of bytes, which is composed of bits, right? So like little zeros and ones, right? So a little 0 or 1 in a computer file to flip it the opposite way, right? Every time you erase that information, there's actually energy that's associated with that erasure of information. The notes that you guys are writing in your journal right now, right? That is like legible information. If you erase that or like burn the paper, there's energy that's associated with the erasure of that information just because it's information, which is a wild idea. But there you go. That's why you can't build a power plant out of just information. So, woo, there you go. That's a crazy one. All right, so you guys ready for quantum walking? It's the other one we're going to do today. Now, I had to shuffle these around a little bit to fit things in the class time, but yesterday, the last one we did was superconductivity. And that's really a setup for this next one, which is going to be quantum walking. Okay, so here we go. I switch over to, you guys remember if you cool down a material cold enough, it could possibly go superconductive, which means there's zero resistance in transmitting electricity. Sorry about that. Let me get this reset. All right. Okay, let's reset that. All right, quantum locking. All right, that's fun. All right, flip back over here. Right. So he's got this superconductor. He's going to put this in a magnetic field. You get these fluxons. These fluxons are magnetic field lines. They're quantized magnetic field lines. Okay. And most of these magnetic field lines get expelled from the superconductor. Right. So draw some field lines. Right, to say over a magnet. Right. And some of those field lines get stuck inside the. Actually, drill them kind of like this is what we did. So some of those field lines get stuck in the conductor, right, lock it in place. So superconductor first. This you guys saw that like look like smoke coming from the superconductor, right? He almost certainly had that immersed in liquid nitrogen. I'm guessing is what that probably was, right? Which is of course crazy cold, right? Crazy cold temperature, right? And then that evaporation you saw was that sublimation as it was going to back into the atmosphere at room temperature. So there you go. All right, quantum locking. All right, I'm gonna stop the recording right here, and that'll be a wrap on class today.